Good morning, everyone. Thank you so much for joining today. Welcome to day 2 of the 2022 Gravitational Wave Open Data Workshop. Today we've got 2 excellent speakers lined up, and I'm really looking forward to their talks. I think without further ado, we can jump straight into it. So our first speaker today is going to be Maya Fishbach. Maya is currently a NASA Hubble Fellow at Sierra at Northwestern University. And she's going to tell us today about the physics of compact object mergers. Maya, thank you so much for being with us today.
Yes, thanks everyone for being here. Let me just share some slides. Sorry, I'm trying to also get it to be in the virtual room here. Okay. Okay, hopefully that is working for people on Zoom as well. Yeah, so I'll just get started. I'm going to give an introduction to some physics and astronomy that we can do with compact binary coalescences. And most of this talk will just be me explaining what a compact binary coalescence actually is. But before I do that, let's just look at this simulation that helps visualize what we're talking about with these compact binary coalescences or CBCs. So here in this simulation, in this movie, you can see we have 2 compact objects, black holes in this case, that are in this binary system. So they're gravitationally bound to each other and they're orbiting around each other in this in-spiral phase, and they're actually getting closer and closer together through the emission of gravitational radiation. So this gravitational radiation is carrying away that orbital energy and angular momentum until those 2 compact objects, in this case black holes, merge. And so these are the kinds of sources that we're talking about with these compact binary coalescences. We can't actually see this happening like you were able to see in the simulation, but we can detect that gravitational radiation, and from that observation of the gravitational waves, infer that this happened. Okay, so what are compact objects? So in the simulation that I just showed, you saw these 2 black holes. There's those black circles. Black holes are the densest objects. So they're so dense that not even light can escape this region outside black holes known as the event horizon. And so they're completely dark because they don't emit any light. A lot of you may be picturing this picture when you think of a black hole. This just came out from the EHT collaboration. This is actually a picture of the black hole in the center of our galaxy, Sagittarius A star. And here you can see this shadow of the black hole. So this light here that you can see is light that is very close to the black hole, but still outside of it, because this region at the center here is the black hole, which does not emit any light. This black hole is actually millions of times more massive than the black holes that we're observing with LIGO, Virgo, and Cagra. But it's, other than being much bigger, it's pretty much the same thing, just this very dense object. So the other kind of compact objects that we talk about and that we're observing are neutron stars. So neutron stars are slightly less dense than black hole. They're kind of as dense as an object can be before collapsing to a black hole. So they're still unimaginably denser than anything we can imagine here on Earth, but they're not completely dark. They're still made up of stuff. And just like the name neutron star suggests, the stuff that they're made up of is mostly neutrons. So neutrons, just like we have in an atomic nucleus, you have neutrons and protons. In a neutron star, you just have a lot of neutrons that are smushed together into these very dense city-sized regions that have a mass of 1 to 2 times the mass of our sun. So here you can see a picture of a neutron star in the center of this supernova remnant. And I'll talk a bit more about what supernovas are as well. So we now know what black holes and neutron stars are. Let me try to this.
Maya, I'm sorry to interrupt.
Oh, yeah.
There's a weird bug of Zoom that things sort of cover up the slides. When you're looking at your screen, do you see like Zoom controls over top of the slide?
Yes, I am trying to hide them.
Yeah,
Okay.
I know it's a challenge.
Okay, that's better, right?
That is better. Yeah, there's still one. Well, I think that's a banner there it goes. Very good. Yep, much better. Thank you.
Okay. Yes. Okay, so those were just some examples of black holes and neutron stars. That's what we mean by compact objects. So either a black hole or a neutron star. And these black holes and neutron stars are made in our universe as the end states of stellar evolution. So when we're observing black holes and neutron stars, we're actually observing this stellar graveyard. And when the way this happens in this extremely simplified picture here is that you start off with a massive star. So you need to start off with a star that's around 10 times more massive than our own sun in order to end up as a neutron star or black hole. And then during that, okay, I'm sorry, I think whenever someone enters the waiting room, my meeting controls come back. Okay, sorry about that. I don't know how to make it stop. Maybe if I stop being host.
Yeah, we can try that. It'll temporarily take away your screen share, but then I'll give it back to you.
Okay.
Actually, I'll tell you what, can you stop your screen share and then I'll try to make this work. Here we go. Okay, so there go your permissions. And okay, you should be able to screen share now. Sorry for the trouble.
Okay, yeah, sorry everyone. I feel like this kind of stuff changes with new versions of Zoom all the time. So still figuring things out a couple years in. But anyway, so we have these black holes and neutron stars in our universe. We know that one way that our universe makes them is from massive stars. So massive stars are around 10 times more massive than our sun, up to hundreds of times as massive as our sun. When they evolve, they actually evolve pretty quickly, and they can have these pretty dramatic deaths. So often these massive stars, when they reach the end of their life, they explode as this supernova and then leave behind a neutron star or a black hole. This supernova explosion phase, sometimes it's not as dramatic. Sometimes the star kind of just directly collapses into a black hole. But that's the general idea, is that these neutron stars or black holes that we're observing are really members of this stellar graveyard. They're allowing us to study what happens to really massive stars in our universe. So that's kind of just a very quick introduction to what these compact objects or these neutron stars or black holes are. the way that we study them is through these gravitational waves, right? So what happens is that when these two compact objects in this binary system coalesce, similar to the simulation that I showed in my first slide, they're sourcing these loud gravitational waves. And these gravitational waves, you can see here, there's these ripples in the space-time. They're perturbations that travel out over space-time from this source and then travel for billions of years across the universe until they reach our detectors. So what this gravitational wave signal looks like, so the amplitude of the gravitational wave is how much stretching and squeezing you have, as you kind of may remember yesterday from Jenny's talk. And as you have this compact binary coalescence, you can think of it as being in these three phases. In the case where you have these two compact objects here, when they're fairly far apart, they're in the in-spiral phase, and so they're orbiting around each other, and you have this frequency of the gravitational wave, which is twice the orbital frequency. So that mostly depends on the masses of your two compact objects. It also depends a little bit on their spins as you get closer and closer during this in-spiral. But as these gravitational waves are carrying away this orbital energy and angular momentum, these two compact objects are getting closer together. So the orbital frequency is increasing. And so the gravitational wave frequency increases as well. And the gravitational waves also get louder and louder as the two compact objects get closer together. Eventually, your two compact objects get close enough together that they actually merge, and you see this spike in the gravitational wave amplitude. And then you end up with this final compact object. In the case where you have this black hole left over, it rings down with a characteristic signal here that depends on the mass and spin of your final black hole. And this final part of the gravitational wave signal is called the ring down. So I mentioned that during the in-spiral phase, you have the orbital frequency and the amplitude increasing as you sweep across time. So you can see that here in this gravitational wave cartoon on the bottom. You can also see it here in the time frequency representation, right? So this is the frequency of the gravitational wave signal as time goes on, and the brightness of these bins here is proportional to how much energy there is at each time and frequency. And so you can see that the gravitational wave signal starts off at early times pretty quiet at low frequencies, and then as it sweeps across time, we increase the frequency and the loudness of that gravitational wave signal. And that sounds like a chirp, which maybe you will be able to hear now. Okay, so hopefully you were able to hear that, but that's what this gravitational wave signal would sound like if you put these vibrations, these frequencies into the auditory band. Okay, so that is just an introduction to what are these gravitational waves from compact binary coalescences. The amazing thing is that we now have many of these actual detections of these compact binary coalescences in gravitational waves. And so that's what you can see here in this poster made by Sudarshan and Karan. And here, each one of these panels represents one of these gravitational wave detections from a compact binary coalescence. The vast majority of these are binary black holes, such as this very first detection here, but there are also a couple of binary neutron stars and even neutron star black holes, so a mixed merger between a neutron star and a black hole that are in this latest catalog that has around 90 events in it. Another way you can visualize these, so that just showed like the gravitational wave chirps essentially of all of those events. You can also visualize this in this animation made by Zohair Doctor of each one of these events. In this case, the ones up to the first half of the third observing run, right? Each one of these chirps corresponds to an actual compact binary. So two black holes or neutron stars, or a neutron star and a black hole in some cases, actually orbiting around each other and participating in this coalescence. So this is great because in addition to just knowing that these black holes and neutron stars exist and that they actually merge with each other, which is quite amazing to realize that that happens all the time in our universe, we can actually learn a lot about these systems and a lot about our universe as a whole. And so the first thing we do is, after we detect the gravitational waves, what you'll hear about in the next lecture is what you'll hear about in the lecture after that tomorrow, which is to actually try to infer what are we seeing. So the gravitational waves are encoding some aspects of the properties of the sources. For example, how big they are. So this is to first order kind of the best thing that we can measure, because this is just setting the overall frequency of the gravitational wave signal, the masses of the two compact objects that are involved in the merger. We can also learn about how fast those compact objects are spinning. So are they spinning at all? Is their spin aligned with the orbital angular momentum, or are they spinning in the plane of the orbit? Then we can also learn about where did they merge. So that's one reason why it's really important for us to have multiple gravitational wave detectors in this network around the world, is that that allows us to localize the mergers better. And so we can actually try to pinpoint on the sky, where did this merger happen? And we can also measure the distance to this coalescence. And then another thing that we can measure in the case of neutron stars is how squishy they are. So the squishiness of neutron stars, because neutron stars are, again, actually made up of stuff, that stuff deforms in a particular way in a strong gravitational way, in a strong gravitational field. And those tides are encoded on the gravitational wave signal. And so we can try to understand exactly just how squishy these neutron stars are. So that allows us to measure these source properties for each event, the fact that those source properties are encoded in the gravitational wave signal. If you look at our catalog of gravitational wave events, then you'll get these plots and tables like this, which in this case are showing these one-dimensional posterior probability distributions on these various parameters. So for example, this first column here is showing the chirp mass of each of these sources that go across this way. And the width of each of these violins here is proportional to the posterior probability at that value. So in this case, for this first event that you see here, GW191103_012549, you can see that its chirp mass was most probably around 8 solar masses, and there's some probability that it was as high as, let's say, around 10 and as low as around 7. So that's what these posterior probabilities mean, and I think you'll encounter them a lot more in the tutorials and also in tomorrow's talks. In addition to learning about individual events, we can then combine this information across multiple events and learn things about the population of compact objects. So I think you'll also encounter this a bit in the tutorials. There are these population models that we then use to describe the distributions of these properties, like the masses and the spins, across multiple of these black hole and neutron star events. So one example of that is to fit a power law to the black hole mass distribution. So in this case, we might say that the merger rate of black hole mergers, it has this shape as a function of black hole mass, where there's quite a high rate at low masses, and then the rate declines with some power law slope up to the maximum black hole mass. So in this case, we use these masses that we've inferred for individual events and combine them all together to try to learn what is the minimum black hole mass in the universe, what is the slope of the power law function, what is the maximum black hole mass. So all of this together allows us to address many questions across physics and astronomy. So I'll just list some example of some questions that we're addressing right now. One thing is, how do the most massive stars live and die? And this is a very general question that we hope to understand about these massive stars in our universe. And we can get a handle on that by looking at things like the merger rate as a function of black hole mass that you can see here. So in plots like this is our inference of what is the merger rate at each black hole mass. These lines, these solid lines here, is kind of the average over our uncertainty on what is the slope of the power law and things like that. And then there's these uncertainty intervals that you see here in blue, which are the 90% credibility intervals on what is the rate at each mass. And so you can see in blue is our latest inference on what is the merger rate as a function of black hole mass, compared to our previous to that inference, which is shown here in the black unfilled contours. And so when we measure something like this, we're learning, okay, what is the merger rate at each black hole mass? But that allows us to answer questions like, how small is the lightest black hole compared to the heaviest neutron star, which is telling us something about the supernova explosions that may give birth to these neutron stars and black holes. Another thing we can try to learn here is, okay, these most massive black holes, how many of them are there? And are they actually made from stellar collapse, or are they maybe made from mergers of smaller black holes, or some other way of making black holes? So another kind of question that we can answer is about neutron stars. So neutron stars are these very extreme laboratories for nuclear physics, essentially. And there's a lot that we don't know about them. So we don't actually know how dense are neutron stars. So how much mass can you put into a given radius for a neutron star? And so that's something that we can try to learn here by looking at how squishy these neutron stars are. So this is our inference from the first binary neutron star event, GW 170817, and we infer these tidal deformability parameters for each neutron star. If these are small, that means that the neutron stars are more compact, so they act more like black holes. You can see that we inferred that these neutron stars were actually quite compact and ruled out parts of parameter space with less compact neutron stars. Another thing that we can learn from neutron star collisions is how the heaviest elements in our universe are made. So in this movie here, you see this animation of two neutron stars merging. In addition to the gravitational waves that they emit really right before they merge, and that's how we're able to detect them in gravitational waves, they also emit this host of electromagnetic radiation. And it's very exciting. We can study kind of all of these many kinds of light that's emitted across the electromagnetic band together with the gravitational waves and try to piece together what happens when these neutron stars merge, because when that happens, you're essentially colliding to a lot of neutron-rich material together, and those neutrons interact with each other and actually synthesize some of the heaviest elements in our universe, like gold and platinum. And so that's something that's also very important to understand when we're trying to understand how chemistry is made in our universe. Another kind of question that we can answer from these gravitational wave observations is about the cosmology of our universe. So one question that we want to understand, because we live in this universe, is how old is it really? And one way to try to do that is to try to understand the expansion of the universe. So we know that the universe is like the surface of a balloon, where every point on the surface of the balloon is actually moving further away from the other points. So from our perspective, it looks like galaxies far away and objects far away at large distances are moving faster with this Hubble velocity. And we can try to measure what is the slope of this relationship. So how fast are objects at a given distance moving? And we can do that with gravitational wave observations in a really unique way, because gravitational waves are telling us the distance to the source that we observe. And if we have some other way of measuring the redshift or the Hubble velocity of that event, like we did in the case of that first binary neutron star event, because we could find its host galaxy and measure that redshift, then we can infer from having both the distance and the redshift what is the slope of this redshift distance relation, which is related to the Hubble parameter, which is then related to the constituents of our universe and also how old it is. So another kind of question that we can address has to do with the fundamental physics of gravity. So we observe these gravitational wave signals, and we can ask, do the gravitational wave signals that we observe actually look like what we expect them to from the theory of gravity, or that we have right now, which is called general relativity? And so there are many different ways that you can test, does this gravitational wave signal look like we expect it to? One example of that is by looking at the gravitational wave signal from each event and then splitting it into the low frequency part of the signal at the early in spiral, and then the high frequency part that has the merger and ring down, and trying to see whether the parameters that we infer for the source from the early frequency part is the same as the parameter that we infer from the high frequency part at the end of the merger. And so we can do that by looking at the final spin of that final black hole, and seeing whether the spin of the final black hole matches the spin that we would predict from the early part of the signal, and same for the mass of the final black hole, whether that matches the mass that we expect from the early part of the signal. And you can see that according to the theory that we analyze them in general relativity, we'd expect there to be no deviation. So we'd expect things to be around zero. And this is consistent with what we infer from analyzing the full population of events. And as we get more and more data, you can see here kind of moving from the dashed to the solid lines, we're getting a tighter and tighter constraint on the fact that general relativity seems to be really, really good as far as describing these events. Okay, so just to summarize this very brief introduction to hopefully what I've convinced you is a very rich scientific field. There's a lot we can learn from these compact binary coalescences. So first, I explained what these compact binary coalescences are, these black holes and neutron stars, which are these compact objects remnants of massive stars. When they coalesce, they source these loud gravitational waves, these ripples in space-time that we can observe in our detectors. The in spiral part of this gravitational wave signal sounds like a chirp that I played. And then this gravitational wave signal through its frequency and amplitude is carrying information about the source properties, like what is actually describing each individual system, the things like masses, spins, distance, and squishiness of neutron stars. And these detections are then able to teach us about many, many different things like massive stars, nuclear physics, cosmology, and gravity. So with that, I'll end my talk and take any questions.
Excellent. Maya, thank you so much. That was great. All right, so we've had lots of questions go by in the chat, which our mentors are furiously working to answer. There was at least one question that we struggled with. Gabriella, I wonder if would you like to read your question out loud, or can I read it? Okay, I'm going to read the question.
Luis Cardenas have a question.
Okay, Luis, if you could put your hand up, we'll call on you in turn. Okay, so we'll start with this one. Maya, on the plot for the deformabilities, what's the difference between the green region and the green, blue, and orange lines?
This plot, I think. Yeah, so I think you can find a lot of the details in the paper. I think from what I remember, these were analyzed under different approximations related to or different assumptions, both about the waveform that we use, because I kind of made it sound like we exactly know what the gravitational wave signal from a specific source will look like, but this is still a very active problem. General relativity is very hard to solve. So we have these different approximations that we make kind of our different best guesses, not guesses, like really rigorous computations for what the gravitational wave signal looks like. But then we also make different assumptions about the kind of other source parameters that are not shown here. And for neutron stars, you'll often see that we analyze things assuming that neutron stars have pretty small spins. So on the kind of allowed range of spin from 0 to 1, or black holes are probably more like 0 to 0.7 for neutron stars. We assume, based on other observations we have of neutron stars, that neutron stars are probably only spinning at less than 5% of the maximum spin. And so I think so overall here, the more shaded regions are just the ones that are more preferred. But I think these different lines that you see here correspond to different assumptions about the spin prior. So what we assume the spins could be, because this is all kind of correlated together with the other parameters in the signal. But I'm not totally sure about that. So maybe someone else can actually can look up what we say in this paper. Yeah. Oh, and these other lines here that you see are different equations of state for neutron stars. So kind of different predictions for what these values should be from theory. And so you can see that some of them are ruled out. So we've actually learned a lot from just this one observation.
Excellent, thank you. And then I see there's a question from the CCA Study Hub.
Hello, can I ask a question?
Yes, if you could put your hand up, if you could use the raise hand feature in Zoom, then, oh, are you from CCA?
Oh, I am from India.
Okay, perfect. If you could use the raise hand feature, and we'll get to you in your turn.
Yeah, no,
Okay.
sorry, feedback.
Hello, CCA, are you there? No? Okay, we'll come back. How about I apologize for the pronunciation. How about Divyansh?
Yeah, that was correct. So, can I ask? No?
Yeah, please go ahead.
Okay, so about yesterday's lecture, keeping aside the unmodeled pipelines, the most part of it of detection of signals from noise was from the match filtering, where we were providing some features about the template. And today, from Maya's lecture, what I can gather is that upon analyzing the signals that are coming, we are also estimating the parameters such as mass and spin. So, isn't it sort of confirming to what we are looking for, or is there something more to it?
Yeah. So that I think that's a really good question. So we do kind of split things up into the detection part, which you'll learn a lot more about in Becca's talk next, and then kind of going in and estimating the parameters. And it's true that we are mainly detecting things in these matched filter searches. So we search across parameter space and generate these gravitational wave signals and then see which ones match the data the best. So the real reason that we then go back in for each event and estimate its parameters kind of again, even though we know, which template it rung up. So we kind of already know that for each event, but we then do a much more thorough job of exploring waveforms across parameter space and looking at the neighboring waveforms so that we're able to fully get this kind of probability distribution on the parameters, as opposed to when we're detecting events and we want to do that very quickly, we're using a fairly coarse grid of waveforms. And so this allows us to kind of zoom in and look at all the waveforms so that we're able to really construct this posterior probability and kind of higher resolution. But you're also right that the choice of what kind of gravitational waves we're looking for in the matched filtering search is affecting a lot of the conclusions that we're able to draw later on. And so there could be gravitational wave signals that are extremely weird, or that we don't have a good idea of even what gravitational wave signal they produce. And so we might be missing those. And so that's why, it's really important to continue to develop gravitational wave signals from even weirder sources and kind of harder to imagine things, and to kind of extend our coverage of the possible parameter space.
Hacerlo chiquito otra vez como Peter.
Okay, thanks, Maya.
Okay, perfect. Looks like CCA Study Hub is next. CCA, are you there? No? Okay. Looks like Manuel is next.
Okay, thank you. Can you hear me?
Yes, you're clear.
Okay, perfect. So I have a question related to the part in which she mentioned about the population, information about the population. So I was thinking that match filter is like a, how to say, it's a template search in which a specific signal is correlated with a complete bank of templates. But my question is, to what extent, if we have enough information about population related to some phenomenological laws, it is possible to optimize the match filter process in order to, for example, to reduce the space of parameters in order to explore the search? This is my question. Thank you.
Yeah. So that's a great question. And this is to some extent something that is being done in different contexts. So yeah, you're right that when we have these multiple events, we're able to combine the information and learn that, most of our events are 30-30 black holes. And so we that affects different pieces of the analysis that we might do. We might then look more carefully for things around 30-30 solar mass black holes. We might, when we kind of analyze events individually, think that, okay, most events are 30-30 solar mass black holes. Let's assume, let's kind of update our prior inference so that we think that any event, even before we've analyzed it, might be closer to being 30 solar masses, for example. We might then think that, when we have a gravitational wave signal that looks like a 30-30 solar mass black hole, even if its signal to noise ratio is a little low, we might think, well, the astrophysical rate of those is high. It's higher than we expect the noise background to be. So let's be more confident that this has a higher probability of being astrophysical origin. So there are kind of different ways that we can carry out this information from the population into the different steps of our analysis. But we don't always do that just because we also want to make sure that we have full coverage over the parameter space of all possible signals, even ones that are rare in the population or even ones that we haven't yet detected a single example of in the population, because those might be the ones where we're actually most excited to make our first detections, are the ones that kind of fall in unpopulated part of this parameter space. So yeah, it's kind of, I think we kind of try to always keep in mind like both approaches. Let's learn from the events we've already seen and try to inform that for our data analysis in future events, but also let's try to be as open-minded as possible to surprises in our data. And that's where we're able to make some of the most exciting discoveries.
Okay, thank you.
Perfect. Thank you so much. Okay, so this has been an amazing discussion. Thank you everyone for the wonderful questions. We are out of time for this discussion at this point. Could we thank Maya very much? However you can, if you can virtually clap or thumbs up or just give her a thank you, we'd really appreciate it. I'm so grateful for her time preparing that talk and sharing with us today. So with that, we're going to go ahead and move on to our next speaker. Our next speaker today is Becca Ewing. We're very lucky to have her with us. She is a graduate student at Penn State. Becca, there you are. Good morning. And Becca, if you're able to share your slides and you can begin whenever you're ready.
Okay, I will share my slides right now. And can people hear me okay?
Yes, you are clear.
Okay, great. All right, so I will now take it over and give a bit more introduction on CBC searches and matched filtering. So here is kind of everything I am hoping to cover today. I'm going to start with just a really brief recap again of compact binary sources and waveforms. Of course, Maya just gave a really great talk on that, but I'll just say a few things that are relevant for the rest of the talk. So first of all, again, as Maya described really well, compact binary coalescences are mergers of the densest objects in our universe. So that means black holes and neutron stars. When these things orbit each other, they're going to emit energy as gravitational waves. And this causes the orbit to shrink and speed up. This makes more gravitational waves be released. And eventually we get this runaway process that leads to the merger and ring down. So we can model these waveforms in sort of 3 stages, the in-spiral, merger, and ring down. And these waveforms for compact binary coalescences really depend on the intrinsic parameters of the source. So that means the component masses and the spins. So you can see in this figure how mainly the masses have a really large effect on the waveform, and in particular, the duration of the waveform. So for low mass systems like binary neutron stars, you can see the waveform might last several minutes. But as we go up into higher mass systems like binary black holes, the waveforms might only be a second or a few seconds long. And so just maybe keep in mind how these unknown parameters really affect the shape of the signal. Okay, so now I will get into a bit of basics about matched filtering and kind of define what matched filtering is. First, I want to give an introduction on the LIGO data itself. What we have is a discrete time series of strain data, and we assume that this data always is going to include a noise component. And then at any time, the data may also contain a signal, but of course that presence of the signal is unknown to us. So we'll also make some assumptions about the noise. First of all, we assume that our noise is going to be stationary. So that means that the noise properties won't change in time. And if you looked at a chunk of data from now versus an hour from now or 2 weeks from now, with the stationary assumption, we're going to assume that those would all be basically identical. The other assumption that we make is that the noise is Gaussian. So this means that if you imagine that you had many, many identical detectors and they were all producing this noise at the same time, you could look at the distribution of those values and you would find that they follow a Gaussian distribution. And then with the stationary assumption also, we can easily say that, no matter what the mean of that Gaussian distribution is, we can easily transform the data to have a 0 mean just by subtracting out whatever the constant mean is. So these are the assumptions we're going to start with. And with that matched filtering, if we have an assumption that we know what the signal looks like, we have basically what we call a template waveform, which is a model of the signal. We can use matched filtering to identify signals in the data. What this is just a correlation of the template with the data. So that means that we're taking the template and we slide it along the data. And at every point in time, we calculate the overlap between the template and the data. And the output of that process is what we call the signal to noise ratio, or SNR time series. And so you can see just kind of mathematically how this is defined both in the frequency domain and in the time domain. And here I have this really nice little movie that was made by Ryan McGee. This demonstrates how matched filtering works. So you can see we have our data in blue, and then we're going to be sliding the template in black along the data. And then at the point where a signal is kind of buried in the data, we get this really nice discernible peak in the SNR time series. And so this, I think, really demonstrates the benefit of matched filtering, which is that, the signal is pretty much invisible by eye. We really can't tell if there's a signal there or where it is. But by using the matched filter, it becomes really clear. And we get this, what we call a trigger, which is a peak in the SNR time series. And so once searches identify these triggers, then we can go on to assess the significance of the triggers. We can form coincidences, which means finding triggers at the same time among multiple detectors. And eventually these become our gravitational wave candidates. All right, so now let's talk about constructing the template banks. So one thing that I glossed over a little bit in the past few slides is that we have this assumption that we know what the signal looks like. We have a template waveform. Of course, for CBC waveforms, we can model the waveforms analytically or numerically, but as I mentioned in the beginning, these waveforms really depend on the masses and spins of the source, which is at the start unknown to us. We don't know what masses and spins we might necessarily be looking for. So we can't just pick one template and match filter the data and be done. Instead, what we have to do is construct what we call template banks, which means basically we choose a parameter space that we're interested in, so a range of masses and spins, and we're going to construct templates covering this entire range, and then we'll filter all of those templates. And so the question there becomes, how many templates do we need to construct? The idea is that if we have a signal that happens to perfectly match the template that we're using, we will get an optimal SNR from the filtering. But any mismatch in the parameters between the signal and our template will cause an SNR loss. So what we do is construct a really dense grid of templates all across our parameter space. And we choose this grid such that any real signal will be close enough to a nearest neighbor template so that our loss in SNR is sufficiently small. We usually just pick some percent of SNR loss that we're kind of okay with losing in the beginning. Maybe something around 3% might be typical. And we construct the template bank to be that dense. And so to make a template bank that covers the full binary neutron star black hole binary, and binary black hole parameter space, we can easily end up with hundreds of thousands to millions of templates that we have to filter. And filtering this many templates is going to pose a really significant computational burden. And so this is something that I'll talk about a little more at the end of the talk, is how do CBC searches kind of handle this computational burden and make the search feasible. All right, so now that I've kind of introduced all the basics of matched filtering and constructing the template banks, I want to go back and revisit some of the assumptions that I made about the LIGO data. So what we had kind of started with was this idea that the LIGO data is stationary and Gaussian. Unfortunately, neither of those are actually true. What we have is non-stationary, non-Gaussian data. And in fact, the only characterization of the LIGO noise that we have is from our observations. And so to get a more realistic picture of what the LIGO noise looks like, what we usually consider is this power spectral density, or PSD, which is shown in this figure. You can think of this as basically a measure of the sensitivity of the detectors. The lower these lines are, the more sensitive the detector is going to be in that frequency band. And this also shows the distribution of the power in the noise across frequency. So the first thing that I want to touch on is that our noise in LIGO is actually colored noise. So this means it has this distinct shape across frequency bands, whereas white noise would have a flat shape across all frequencies. And so what we want to do before filtering is to whiten the data and the templates, which basically means dividing out this PSD. And so that's shown here in these equations, and then we'll indicate a whitened quantity by this little hat. And so when we do the matched filtering, we're actually doing it with the whitened data and templates. Okay, the next property of the noise is non-stationarity. So first of all, the LIGO noise can and does vary over long time scales. So that means it could be hours to days or week time scales. And this can just be affected by lots of things. Maybe human activity or the weather even could affect this. And so the way this affects the searches is that basically in order to whiten our data, we need this measurement of the PSD. If the data was truly stationary, we could just measure the PSD once and know it forever and always use that one PSD. But since the noise properties are going to be changing in time, the searches have to continuously track the PSD and remeasure it and keep updating that quantity so that we can whiten the data accurately. The next property is non-stationary on short timescales. So these are what we refer to as glitches, and they're basically just short duration, non-Gaussian artifacts in the data. You can see what it looks like if we are matched filtering data that includes a glitch in this video here. And glitches can be really a big problem for matched filtering searches because you can see how even though this glitch really looks nothing like a real signal, it can still ring up these really loud peaks in the SNR time series. So the real CBC searches have to find methods of distinguishing these glitches from true signals. And that's another thing that I'll talk about in the rest of the talk. Oops. Okay, so now for the rest of the time, I want to go into some more details on the implementation of these matched filtering searches with the real search analyses that we have. So GST-LAL, MBTA, and PyCBC are the three that I'll talk about. And I'm going to just mostly focus on GST-LAL because that's the one that I work on. But I'll also talk about a few of the differences in the way that MBTA and PyCBC do matched filtering. So in practice, the search pipelines have this problem of dealing with the non-ideal noise properties that I just introduced. And additionally, they have to find ways to make the search efficient and deal with this computational burden of filtering maybe millions of templates, and especially trying to keep up with the data and do that filtering in real time. And so first, I will talk about how GST-LAL handles all of this. So first is handling the non-Gaussian data. I'll discuss kind of three different solutions to this that GST-LAL uses. The first one is gating. This is something that's done before the matched filtering. So what this basically is that we look into the data and we find things that look like glitches. And if we see something that looks like a glitch, we can just take a small chunk of time around that data, replace that data with zeros, and just decide that we're not even going to filter it. We'll just remove it because it looks like a glitch and it's basically too dangerous. This can be a really powerful way of dealing with the non-Gaussian data, but the immediate problem is that we have to be really careful not to accidentally gate a real signal. And this can be especially a problem for the higher mass templates. So think about really heavy binary black holes. These can have waveforms that are extremely loud and very, very short, and they may only last a few cycles. And so these are really easy to kind of mix up with glitches. They really look very similar. And so this can be a big problem, is accidentally, gating a heavy binary black hole waveform because we thought it was a glitch. And so because of that, kind of the second way that we handle this non-Gaussian data is with signal consistency tests. So this is something that's done after the matched filtering. The idea here is that from filtering, we don't just get this one single SNR peak and that's all we have. Instead, we have the full SNR time series. So if we imagine taking a template waveform and we assume that we have a signal in the data that precisely matches that template, then we can make a prediction for what the SNR time series from filtering that data will look like. We can basically know ahead of time what signal shape we expect. And then from filtering the real data, we can compare the measured or observed SNR time series to that prediction. And for a real signal, we would expect to see that the measurement matches the prediction. Here you can see just an example of that in this plot. The blue line is our prediction, and the black line comes from matched filtering, a stretch of data where we've injected a known signal into the data. And so you can see in that case how well the SNR time series match. And so this gives us an indication that the signal is real, whereas for a glitch, the SNR time series would not look how we would predict. So the third way that GST-LAO specifically handles non-Gaussian data is with IDQ. So IDQ stands for Integrated Data Quality. The idea here is from our detectors, of course, we have our main strain channel where the gravitational waves show up, but we also have many other auxiliary data channels, and these can monitor lots of other information about the state of the detectors, but they're kind of blind to gravitational waves. So what IDQ does is it monitors these auxiliary channels and uses machine learning to assign a probability that at any time there is a glitch in that data. So then with GST-LAO, we can take those probabilities from IDQ and use them to either increase the significance of our candidates if IDQ tells us that this data looks clean, or if IDQ tells us that there's very likely a glitch, we can reduce the significance of our candidates. And this is something that currently is only used by the GST-LAO pipeline. Okay, so that's kind of how GST-LAO handles this non-Gaussian data and the noise properties. Now I want to talk about how GST-LAO handles this computational burden of matched filtering. What we use is called the Lloyd method. This stands for low latency online in-spiral detection. And this method was developed for the purpose of enabling real-time matched filtering and even early warning matched filtering. So what that means is that we're able to identify a signal in the data even before the merger occurs or before the coalescence time of the signal. And so this method consists of two sort of steps, which I'll talk about in more detail, but they're first time slicing and downsampling of our waveforms. And then second is what's called singular value decomposition, or SVD. And the whole idea of this method is just to reduce the computational burden, improve the efficiency, and ultimately lower the latency of the search. So the first step is the time slicing and downsampling. Here we are taking advantage of this CVC waveform property, which is that they all monotonically increase in frequency. So with time, the frequency is always increasing. The idea is that in order to accurately represent any waveform, you need to sample it at a sampling rate that's at least twice as high as the largest frequency component in your waveform. But if we sampled these waveforms at twice of 4096 hertz, that means that for this lower early part of the waveform, we would be severely oversampling it, which is just extra unnecessary computation. So instead what we do is we take these template waveforms before the filtering and we split them into time slices. And each of these bands has a different frequency range. So at the early part, the frequencies are really low. And then in this next range, they get a little higher. And at the end, we have the highest frequencies. In each of these slices, we can downsample. And so use a much lower sampling rate down here at the early parts of the waveform compared to at the higher part of the waveform where we have to use the full sampling rate. And this downsampling is really, really helpful to improve the efficiency of our search. Make sure that we're not doing unnecessary computations by oversampling the waveform, and it makes it possible to perform this matched filtering in low latency. So the next half of the Lloyd method is the singular value decomposition, or what we call SVD. So here we are taking advantage of the template bank property. So if you remember, we construct these template banks to be extremely dense over the full parameter space so that we can make sure we are not losing very much SNR. But because the template banks are so dense, we end up with a lot of redundant templates. They all look really similar, and maybe from template to template, there's just a very small change. And so if we filtered all of these, it would be a pretty redundant process. So instead, what we do is you can think of each of these waveforms as just a vector, and the full set of these waveform vectors covers the space of the parameter space that we chose. What we can do is reduce the set of vectors to a set of basis waveforms, which still cover the space, but all of the basis waveforms are linearly independent. And so there's a much smaller number of them. The set of basis waveforms can maybe be at least a factor of 10 smaller than the original size of the bank. And here's an example of what those basis waveforms might look like. They have these kind of crazy shapes that don't look physical at all, but they're all much more unique. And so we get rid of that redundancy. So the idea with SVD is that we can perform our matched filtering with these basis waveforms. And then at the end, we can reconstruct any of the original input templates by just doing a linear combination of the basis waveforms. And at the end of the day, this saves us computations. And this is really key in allowing us to do that real-time matched filtering. Okay, so now I will just briefly kind of talk about MBTA and PyCBC and the differences in the way that these searches do matched filtering. One of the main differences is that PyCBC and MBTA both regularly perform matched filtering in the frequency domain, whereas GST-LAL usually does matched filtering in the time domain. So the idea here is that if you're matched filtering in the time domain, to get the output or the SNR at any point in time, you have to do a convolution. You have to do this integral. But if you transform to the frequency domain, that convolution just becomes a multiplication. And so what MBTA and PyCBC do is they first take the time series data from the detectors. They do the fast Fourier transform on the data to get it into the frequency domain. Then you can filter just by doing this multiplication, and then fast Fourier transform back to get the SNR time series out. Okay, so then how do MBTA and PyCBC handle the non-Gaussian data? In a lot of ways, they do it similarly to GST-LAL. So they also use gating and the signal consistency tests. But each pipeline might differ in the kind of very technical implementations of these methods. And then the other thing is that MBTA and PyCBC don't use IDQ, but instead they use vetoes. So these are basically flags that are applied to stretches of the data, which indicate kind of our confidence that the data is clean or whether it includes a lot of glitches and it's basically not suitable for matched filtering. So MBTA and PyCBC use vetoes to determine when data has poor data quality, and they can use that information to assess their triggers. The other thing that MBTA does is they refilter all of their high mass templates without using gating. So the reason for this is because, like I said earlier, it's really, you have to be very careful with gating not to accidentally remove true signals from the data. And this is especially problematic for those really heavy binary black hole waveforms that can tend to look a lot like glitches. So in order to account for this, basically, MBTA will refilter all of those templates without gating first, so that they can be sure that they're not missing those signals. Okay, and then lastly, MBTA does what's called multi-banding. This is really similar to GST-LAL's time slicing method. And in fact, the time slicing of GST-LAL is based on this multi-banding from MBTA. What they do is they filter the data in two frequency bands, so a low frequency and a high frequency band, and they can construct their templates then in this low frequency and high frequency band. So they have two sets of templates and they filter them separately. And then at the end, they can reconstruct the real templates after the filtering. And again, it's the same idea as the time slicing. This just allows for a reduction in the computational cost of the filtering and allows the whole process to proceed much faster. Okay, so as a summary, CBC searches are looking for gravitational waves from merging black holes and neutron stars in the LIGO Virgo strain data. We are able to use matched filtering for these searches because we know what the waveforms will look like. Because we're able to model them, we can construct templates and then do this correlation between the template and the data in order to identify the signals. And we have the three real matched filtering searches, GST-LAL, MBTA, and PyCBC. And these each have their own technical implementations and methods in order to perform the matched filtering, improve the sensitivity, and reduce the computational cost of the search. So that's all I have, and I can take any questions.
Awesome. Becca, thank you so much for the great talk. Actually, I've already seen a few comments appreciating your talk and how clear and thorough it was. So thank you so much. Maybe we can give some applause, give some thanks to Becca. That's possible. Okay, perfect. And we've already had a lot of great questions in the chat and also on the discussion forum at ask.igwin.org. And so we'll look now for hands up. I did see that Luis raised his hand earlier in the chat, so maybe we can start with him.
Okay, congratulations, Professor Ewing. A great lecture. I would like to refer to the event GW 190A14, an event of a great gap. I mean, there is a controversial about the nature of the little object M2, less than 3 solar masses. I would like to know your opinion about the nature of this object. It is a little black hole, it is a great neutron star, or it is a new kind, like a quark star. The thing is getting worse because Professor Abbott, in the last request in the Rune 03B, discovered 4 new events with the same features. The W191219, the event 200115, the event 200210, and the event 200105. So we have to learn a new strategic to find this controversy. I would like to know your opinion. Sorry about the question, sorry.
It's okay. Okay, so first question I think was about GW 190814, which was one of the systems that we found that has this secondary component where the mass is in this uncertain range. I think you mentioned it could either be a heavy neutron star or a light black hole. I take a pretty agnostic opinion on this. I think ultimately we're not sure. It's likely to be a black hole, but I think we really can't make a certain statement on that yet. But I think maybe in 04, when we're making more and more detections, it's possible we'll find more systems in this range, and maybe at that time we can get a better sense of what the true nature of these sources are. And then the other sources you mentioned were all of the kind of NSBH or potential NSBH systems that we found in O3b. That was one of the most exciting things about O3b, because we had never confidently detected an NSBH system before. I think the most confident one that we found was GW 2001-15, and then there were a couple that were a little less certain. But I think each of them were really interesting events, and definitely in the future we can go back and do more follow-up on them and get a better sense of each of the nature of those sources.
So the mystery continues.
Yeah.
Okay, I love you. Thank you.
Okay, perfect. Thank you, Luis. Let's see, we've got our next question is from Purnima.
Hi, Becca. So I have a question about incorporating the missing physics in the templates. So from my understanding, or to my knowledge, I think we have still not included effects like eccentricity, effects of gravitational lensing, and there are still a lot of missing physics. So though we have a high number of templates to the power 10 to the power 5, 10 to the power 6, what is stopping us from making more advanced templates incorporating these missing physics?
So that's a good question. I think my understanding is basically, for one thing, if we wanted to include these other regions of the parameter space in our template banks, that would significantly increase the size of the template banks, and that can be a problem for us. Additionally, I think with some regions of the parameter space, like for example with precession, including these templates in the original search doesn't actually improve our sensitivity that much. It doesn't really help the search be more effective. So it can be a good idea to just basically leave the template bank without those regions. And then at the end with the parameter estimation, which I think you'll hear more about tomorrow, those regions can be explored a bit more.
I understand. Thank you.
Okay, perfect. Let's see, our next question is from, I apologize for the pronunciation, Divyansh.
Yep, you pronounce it right. Can I ask?
Yes, please go ahead.
Yeah, regarding that parameter space that we were talking about, Rebecca told that we take a vector and we sort of choose from the redundant ones and create a vector where we have the independent vectors to that would entirely make the parameter space. So how do among the redundant ones that similar parameters vectors, how do we choose the one among them? Do we average it out or something? What's the approach?
So let me go back to that slide if I can. So I think, I hope I understood your question correctly. Essentially, what happens is we get this reduced set of the basis waveforms. The full set of them will cover completely the entire parameter space. But what we can do is kind of rank them by their importance sort of in recomputing the original templates. And so we might just choose some accuracy of the reconstruction that we're okay with. So say we want to reconstruct any of the original templates to 99.9% accuracy, then we can just choose the basis waveforms that are required to get that amount of accuracy, and we can ignore the rest of them. Some of them, might just have a really, really small impact on the reconstruction. And so then we filter all of those waveforms that we need in order to do the reconstruction And then at the end, we can reconstruct the physical templates.
Okay, thanks, Rebecca.
Very good. All right, so I think we will draw this part of the session to a close. So let's thank Becca one more time. And thank you everyone for the excellent engagement and questions. I saw a lot of great questions in the chat, a lot of great questions asked out loud. Also, thank you to our mentors for monitoring the chat, and also the ask.igwin.org discussion forum. I've seen a lot of great responses get posted there as well. So thank you all. So with that, I'm going to pivot, and we'll spend just a few minutes talking about the tutorials for today. So I'm going to try and take the screen share. Let's try that. Okay, very good. So hopefully, scooch this over. Hopefully now you can see my browser. And if you're looking at the workshop webpage, if you scroll down to tutorials and online course, you'll see a button for online course. I know that several hundred of you have already found it, so that's great. But if you haven't, here it is. And you can click that, and it'll take you into the Thinkific platform. If it's your first time using Thinkific, then you will need to create an account. But the course is free, so we do welcome and encourage everyone to come in, enroll in the course, and access our tutorial material this way. On the left menu bar here, you'll see a number of different modules for the course. Yesterday, we focused on data access and working with GWPy. So today, we're focusing on CBC sources and searches. And you'll see that under there, there's a number of tutorials and activities. The modules or the lessons that are marked tutorial, when you take a look at those will include these buttons to launch our Jupyter notebooks. And so you can use these buttons to launch directly, or you can go over to the GitHub and you can follow instructions if you prefer to run the tutorial locally on your computer. Once you load up an online resource, you'll see something like this. There's a tutorials directory. Under the tutorials directory, you'll see day 1, day 2, or day 3. In this particular lesson, I'm looking for tutorial 1.4. So that 1 is going to correspond to day 1. So I'm going to come into day 1. I'm going to find tutorial 1.4, and I'll click that to open it up. And then these cloud resources, these are interactive live environments. So you should be able to run the tutorials here. You can add cells, add code, and edit. As you get down to the bottom of so you'll find lots of good information here, walking you through steps to try out some of the concepts that got talked about today in the lectures. And then as you get down to the bottom, there are even some exercises. Those exercises will more or less correspond with the activity questions that are here in the Thinkific. So inside the Thinkific, when you click activity, you'll see something that looks like a short quiz. So you can look at the challenge questions there. You can look at the questions that are inside the notebook here. You can actually use the notebook to try to answer the quiz questions. So you can type new code here in the notebook. And so if there's a question that can be answered with some lines of code, you can use the notebook itself to write some new code, cut and paste code examples from above, and answer the questions in that way. So hopefully today, with your study hubs or on your own, you'll focus on the day 2 tutorials or this CBC sources and searches lesson here in the Thinkific. And hopefully you'll have a good experience with that and be able to learn. Of course, if you run into questions, you're welcome to ask mentors at your local study hub. Or as always, questions can be posted into the discussion forum at ask.igwin.org. That is all of my notes for today. Thank you all so much one more time for a great session. And we will, is there one more question for Nima?
Yes, I'm sorry. I had a final question. So Are we supposed to finish all of the tutorials in this 3-day period, or do we have a little bit more freedom to finish the data challenge and get the certificate?
Yeah, that's a great question. So, these tutorials and materials will all remain available after the workshop. So, of course, you're welcome to work with them at any point. We are setting a goal of completing the data challenge by 1 week from the end of the workshop. So the third day, the last day of the workshop will be tomorrow. 1 week from tomorrow, I believe, is June 1st. And so we are setting a goal to complete the data challenge solutions by 1 week after the end of the workshop. Any data challenge solutions that are submitted by that deadline, we will make an effort to score them and see see if we're able to pick a winner this year. But the materials will remain available. And so if this week is a bad week for you and you prefer to work on them at a later date, that's of course fine too.
Sounds good. Thank you.
Okay, good. Any other questions for today?
Hey, Jonah, is there a certificate in Thinkific?
Yes, that's correct. So in the Thinkific, when you complete a module, you'll get a little check mark here. And then once you've worked through, and the last module is actually the data challenge. We'll talk about this tomorrow, but the data challenge is here. And right here is the item to submit your data challenge solution. I believe you can only do that once. And once you've worked through all the modules and gotten a little checkbox on all of them, then Thinkific will give you this option to download a certificate.
Congratulations for Luis. Great job, Professor Kanner, as always.
Perfect. Thank you, Luis. That's very kind. All right. Okay. Well, thank you all very much. And I wish you good luck on the tutorials.